So let's look at an example where we can kind of see how fast do we need to be going. So here's a roller coaster. It has a loop with a radius of 15 meters. I want to know how fast does the cart need to be going at the top here to ensure that the people don't fall out, even if they don't have seatbelts on. So press pause, see if you can work through this. Draw yourself a free body diagram, write a net force equation, see if you can make sense of all that, and then press play when you want to go through it with me. So let's draw a free body diagram in this perspective, and I'm going to draw it for when the object is at the top of the cart. So in this case, the R direction, which points from the object towards the center, the positive R direction is straight down, and the positive T direction is to the left. When they're in this position, the forces that are acting on them are going to be gravity pulling straight down. Gravity always pulls straight down. And the normal force of the bottom of the cart on their butts, their seats on their butts are pushing them straight down. So I can say my net force in the R direction. Remember, downwards here is the positive R direction. So that's N plus mg. Those are the pointing down. My net force in the R direction is always equal to my mass times my acceleration in the R direction. And my acceleration in the R direction is equal to v squared over r. So here's the v. That's what I want to know. How fast does this need to be so that they don't fall out? Well, let's think, what does it mean if they fall out? What does it mean about the normal force? One thing I can look at this picture and I could say the faster we're going, the bigger v is, the bigger the normal force will be pushing you down. Because if you're making this curve at a fast, fast, fast speed, you need lots of force to push down on you. Gravity is not going to change how big it is, but the normal force can push down with more and more and more force. If you're going through here super fast, the normal force is going to push down on you really, really hard. So as v gets bigger and bigger and bigger, n is going to get bigger and bigger and bigger. Okay? Well, what if v gets smaller? What if we do this loop but we're going really slow? If v gets smaller, then the normal force just will not push down with as much force. Well, what if v is so small that we get to the point where the normal force is 0? That would be like if you round this loop-de-loop and right when you get to the top, your butt leaves the seat just for a split second while you then move forward and continue the ride. That would be a normal force of 0. And you cannot go slower than that. Because if you go slower than that, if this number is too slow, then gravity is going to be pulling down on you more, and you're going to actually fall out of there. So the smallest that the normal force could ever be is 0, and that's the slowest you can go and still complete the loop. The minimum speed that we can go is when the normal force equals 0, because the normal force can never be negative. The normal force can never pull up on you. So the smallest you can go is when you are you're going just slow enough so that right when you're right at the top, you're in free fall for a split second, but then you keep going forward, and in the next moment the normal force is going to push on you. So that would be when n equals 0. That's the minimum speed. So let's see what that speed is. Okay, so if I plug in 0 for my normal force, the mass cancels, so that doesn't matter how much you weigh when you're going through here. The mass does not matter. Mass cancels out. And here, what I've done is just solve for v, because this is something special here. We can call this v sub c, which means this is a critical speed. Critical speed means, it's special. This value of the speed is special. It's critical. If you go slower than this speed, you will fall out of your circle. If you're spinning a pail of water and you spin at the very top, that bucket of water goes slower than that critical speed, then the water is going to fall out onto you. Okay. So the critical speed is equal to the square root of r times g. Again, this is the critical speed needed at the top in order to complete the circle. It's independent of the mass. This is for anything that's traveling in a vertical circle. This is the critical speed that it needs to complete that circle. In this case, I can plug in that my radius is 15 meters and we're on Earth, so that speed is 12.1 meters per second, which is not very fast. So most roller coasters, you're going much faster than that anyway up here, which is fine to go faster. It just means the normal force is going to push down on your butt with more force. This speed is pretty small speed. Incidentally, this equation also can tell you if you're going on top of a circle, like if you're driving over a speed bump. Oops, let me go back. Sorry. If you're driving over a speed bump, this equation can tell you how fast you can go so that you don't catch air. Because if you go too fast over a speed bump, you catch air at the very top. That's when the normal force would be equal to 0 at the very top. And This also, so you can use the radius of the speed bump and take the square root of that, and that tells you the critical speed so that you will not catch air over the speed bump. Here's one more example. This is a car driving over a circular hill, and I want you to compare the normal force on the car to the weight of the car. So press pause, think about it, and then press play to see the answer. Okay, so again, this is an object moving in a circle. Whenever an object is moving in a circle, the object is always accelerating towards the center of the circle. So when this car is at this point on the circle, it will be accelerating towards the center, which is straight down. So at this moment in time, the car is accelerating straight down. There's a normal force pushing up and gravity pulling down, but there has to be a net force pulling down. So in this case, the normal force has to be smaller than the force of gravity, or smaller than the weight, okay, which is B. If you go through this fast enough, you can get to the point where your normal force is 0. That's where you catch air over the top of this, okay, and then come back down. So if you're going fast enough, that normal force will be 0. But at slower speeds, what we definitely know is the normal force will be less than the weight. That's why when you're in a car, if you ever drive over a bump like this, sometimes you get that feeling like your stomach drops a little bit, or you might feel like you're rising up out of your seat. You are feeling the normal force decrease. You're feeling your butt, your seat is not pushing up on your butt as much when you're right at the top there. And the faster you go, the smaller the normal force will be, so your seat will be pushing up on your butt even less. And then your intestines are pushing up less on your stomach. The normal force on your holding your stomach up can be smaller right at the top here. So you feel that in your stomach. You feel that smaller normal force pushing up on your stomach right at the top there.